Hi, thanks for watching. This is Tengyu from Stanford University. This is based on joint works with Kaidi, who is a student at Stanford University and who is also the lead author of two of the papers that I'm going to talk about. And also Yiming Chen and Colin Wei, who are PhD students at Stanford in my group, and Nichols and Adrian, who are researchers at Toyota Research Institute, and also Jun Wei, who is an assistant professor at Harvard University. The topic of this talk is going to be about imbalanced and heteroskedastic datasets. And the techniques we're going to introduce is about adaptive regularizations. Let me start by talking about the motivation of these works. One of the challenges we are trying to address is long-tail distributions. Probably some of the other speakers also talk about the motivation of it. I'm just going to quickly give a few examples. So the challenge is that in real-world dataset, the training data is often imbalanced, but the test data are often balanced. For example, this iNaturalist dataset, which is held at CBPR 2019, I think there's a 2020 version of it as well. So the number of species is 1,000, and the distribution of the number of images per species is pretty long-tailed. You can see that the number of images per class can range from 500 to 50. And here, the test data is designed to be balanced, because if you have imbalanced test data, then the rare classes will be ignored, just because ignoring them wouldn't hurt your accuracy too much. So that's why we care about a balanced test data, but imbalanced training data. Another example is semantic segmentation. Here I'm having the distribution of the pixels per class in the cityscape dataset, which is one of the commonly used dataset for semantic segmentation. And here you can see that again, the training distribution is pretty imbalanced. And here the interesting thing is that the test distribution is also imbalanced, which is the same distribution as the training distribution. However, the test metric are balanced, because the test metrics are the mean of the per class accuracy. You are computing the accuracy for each class, and then you take the average over the classes. And also another common metric is the mean of the per class intersection over unit, which is also a balanced test metric. And here, one of the interesting things is that there are actually a few classes in the original data set which are so rare that they are not even included in the common benchmark comparisons. So this also suggests that rare classes are pretty hard to learn in these imbalanced data sets. There are many other scenarios where you care about long-tail data sets. For example, in imitation learning, the rare actions are so crucial, so they cannot be ignored. And in healthcare, there are different kinds of imbalances across groups from different regions, different races and ages. And also this raises fairness concerns, because you want to do the best for all of the regions, races, and ages of all of the subgroups. And also in NLP, I know that this is a vision conference, but in NLP, the distribution of words is also long-tailed, and the rare words might provide a lot of information that shouldn't be overlooked. So what are the issues of learning this kind of imbalanced data set? I think there are two main issues. One of them is that the minority classes have worse training error, and the other issue is that the minority classes have worse test errors. Here I'm plotting the accuracy, the validation error, and training error of the classes for the cityscape dataset, and I'm sorting the classes from high frequency to low frequency. And as you can see that when you have low frequency classes, the validation error and training errors both tends to be higher. So it turns out that there is a relatively easier part of the story, which is fixing the training errors. So it's not that hard to fix the training errors. So what you can do is basically resampling or reweighting the stochastic within descent algorithm, which is kind of a classical technique. So what you do is you sample the classes uniformly, and then you sample the examples uniformly conditioned on the classes. This way, you're going to upweight the rare classes and also downweight, effectively downweight the frequent classes. As a result, rare classes are trained more often, which means that you are fixing the training imbalance. And here is a figure showing some toy cases where you have a CFAR10 data set. We're training on the so-called imbalanced CFAR10 data set where we downweight 5 of the classes. So here 5M, 6M, 7M, and up to 9M. These are 5 classes where we made them to be minority classes, where I think we just drop 90% of the examples from these classes to make an imbalanced data set. And then you can see that if you train with ERM, empirical risk minimization, meaning you have the same weights for the same number for all of the examples, then the training error is pretty high for all of these minority classes. However, on the other hand, if you do the rebalancing technique, if you do the resampling technique, for example, introduced by one of these paper by Cui et al., class balance loss based on effective number of samples, then you can see that the training error will be much better for these minority classes at the expense of a little bit higher training error for the frequent classes. So this effectively fixed the training error issue, and there are many different ways to reweight your examples, according to different formulas, and they all tend to have similar effect, meaning they make the minority classes train much better and at the expense of a slightly worse training error for the frequent classes. However, it seems that the harder part of the story is that actually the minority classes also have an overfitting issue, which is not super surprising because we have fewer examples in the minority classes. As you can see in this figure, so after we do the resampling technique, we can improve the training errors for the minority classes, but it's harder to improve the test error for the minority classes. The test error does improve in general for the minority classes, which could be attributed to better training errors. However, the gap between the test error and training error for the minority classes is still pretty high. So the second challenge in this talk that we are trying to address is the so-called heteroskedasticity in the data sets. So let me just briefly review the definition of heteroskedasticity, which is a commonly used notion or concept in classical statistics. So heteroskedasticity means that y given x, the observation or label given x has a varying level of uncertainty. Or maybe more technically, the entropy of y given x or the variance of y given x heavily depends on the choice of little x. So here is a typical example of heteroskedastic data set. So you have this linear function, which is the true function. However, the noise depends on which x you choose, right? So the larger the x is, the noise level is bigger. So that's why it's heteroskedastic. So you may wonder, why the real data set have heteroskedasticity. So I think there are several different reasons. So one of them is that the observed annotation are noisy, and the noisy process is pretty complicated. So naturally, there is a varying level of noise for different examples. So recall that even though, let's say, suppose there's a true label for each of the images you care about, then actually still the annotation you got, the human labels you got, is a function of both the true label and the image, right? So there could be some noisy process caused by the human labeling, right? So, and this noisy process can depend on the class and example. And many of the prior works on noisy data set do assume that there's a uniform random noise from Z to Y. So you basically uniformly change the true ground truth to a random other classes. So this, ignores the heteroskedasticity from this noisy labeling process. Some examples might be harder to label, and some other examples might be easier to label. Certainly, not all the examples have the same level of noises in their labels. And in one of this web vision data set, which is web crossed, so you can see actually they plot the amount of ambiguity or kind of like a labeling noise in their data set, and you can see that here 3 votes means that there is no ambiguity or labeling disagreement, and you can see that the number of 3 votes can changes quite differently across the categories. I guess as I alluded to a little bit, so there are also ambiguous examples, right? So even though there's no noise at all for your example, right? So there's a unique, the labeler is actually doing the right thing. Still, there's ambiguity, intrinsic ambiguity in the examples. For example, here I'm having an image here, and you may wonder whether the true label should be horse or person or horse person, right? So there could be 3 labels in some sense, but if you just have to choose one, then probably the right label should be from a distribution of horse person and horse person, right? So how do we address this kind of stochasticity or like a heteroskedasticity in a noisy data set? So one of the common technique is called, can be summarized as detecting the noisy examples and then delete the noisy examples. So there are several different works, along this line using similar kind of ideas. I'm describing one work that I'm familiar with, that I'm involved in. So the idea is that you use a large learning rate, then a noisy example tends to have larger training cross-entropy losses. So this is a plot in one of my work, which is actually appears in this conference. So this is a joint work with Jiaming Song, Lun Jiahu, Michael Olli, and Yan Dolphin. So we show that if you have a synthetic noisy data set, here you can see that if you plot the training distribution, the histogram of the training losses, then you can see that the noisy examples tend to have much larger noises than the normal examples. And if you have some threshold, then you can pretty much tell them apart approximately. So this motivated the following algorithm, which is very, very simple. It's so simple so that it's a little bit harder for us to make the paper get in, just because it sounds like too simple. So the algorithm is just that you detect noisy examples using large learning rate by taking the threshold. There's a formula for computing the threshold, and then you delete all the examples with larger training losses, and then you continue to train. And potentially you have to decay your learning rate, because that's the only way you can get to a very high training accuracy. So we wrote this paper 2 years ago effectively, and still I think after 2 years, this is one of the best methods for noisy data sets. I highly recommend it. It's very simple to implement. And there are indeed many other similar works that does similar kind of filterings based on the training losses. So this sounds like generally a good idea. You kind of reweight your examples in one way or the other based on the training losses. But however, there is a big issue when you use these kind of techniques on imbalanced and heteroskedastic datasets. So the issue is that it's very hard to distinguish noisy examples from rare examples. So we have seen that noisy examples tend to have bigger losses. However, on the other hand, rare examples and clean examples also tend to have other bigger losses. Even though the examples is pretty clean, there's no label noise, still just because the example is rare, sometimes it tends to have bigger losses. And if you create this imbalanced and noisy synthetic CFAR10 data set, so what we do is we say we inject some uniform level of noise for all the classes, and also we make the number of examples per class imbalanced. So I think 5 of the classes are considered to be rare. They have much fewer number of examples compared to the other classes. And then if you plot the distribution of the training losses for the rare classes and the frequent classes, and the rare clean, rare noise, frequent clean, frequent noise examples, then you can see that generally it's true that noisy examples tend to have larger losses and rare examples tend to have larger noises. That's true. However, there's no unique threshold that can tell apart noisy examples from the clean examples. For example, if you take the threshold too large, then you are not going to detect those frequent noisy examples. If you take the threshold too small, then you are going to confuse the frequent, the rare clean examples with the rare noise examples, because they all have relatively larger training losses. So this, this becomes a problem, especially when the data set becomes more and more imbalanced. And there's another related issue, which is that some of the mislabeled examples probably shouldn't be dropped, just because they are still useful in some sense. So here is an image, which is a dog. However, if you imagine that maybe the label of this image could be a fox, just because this example seems to be pretty ambiguous, and maybe the labeler didn't, carefully look at the background of the couch, and then just to say this is a fox, right? Just because the dog looks like a fox. However, whether you want to just discard this example, as we have seen in the work that I was talking about, so the algorithm there will just try to discard this example because it's not correctly labeled. However, if you think about it, a label fox still tells you something. It's not perfect. It's not as perfect as dog. However, label fox also tells you that actually this image is not a fish or airplane or something else, right? It's still a mammal. It's a cute animal. So that still gives you some information, probably that you shouldn't drop. So maybe you just want to weigh down these mislabeled examples, for example. You may think that's probably the right thing to do. You don't want to just discard the example, but just weigh down. However, in the previous work that I've just talked about, the reason why we discard the example completely is because if you're just downweighting the hard examples or the ambiguous examples with larger training losses, then actually it's even easier for you to fit it's easier to overfit to the training examples. So actually smaller ways will make it easier to fit to those examples. So actually sometimes you may get into exactly the opposite effect. You want to discard this example or consider this example less. However, by downweighting the example, sometimes you can, and pretty often, you can overfit to this example even easier. So as you can see, so we have these two challenges about imbalanced and heteroskedastic datasets, and they are somewhat intertwined because when you have both of these two issues, some of the techniques becomes problematic. And the idea that we are proposing here is to regularize the model instead of changing the weights of the losses. And here there's as you will see, regularizing the model can provide a unified way to deal with ambiguous examples, mislabeled examples, noisy examples, so on and so forth. So using regularization is pretty common idea. There's nothing fancy about it, right? It's a common idea for small and noisy data set. And also using regularization is still useful for deep learning, even though we don't use very strong regularizations typically when you train the benchmark data set like CFAR ImageNet. But still, especially when you lack implicit regularization and when you have this kind of slightly different heterogeneous kind of data sets, it has been shown that using explicit regularization is still pretty useful, and especially when your data is small. And also, regularization can mitigate the so-called double descent phenomenon, which I'm not sure some of you have heard of. Maybe some of you have heard of. So the double descent phenomenon means that if you plot the test error against the number of data points you have, then you can see that actually it's not like monotone or kind of like actually, it's not true that more data is always better. Sometimes, you have this double descent curve of the test error in the number of data points. And so, however, if you add regularization, then this double descent curve mostly are gone, as shown in this paper with Nakaran. And regularization does help a lot in improving the test error for those small number of data points cases. And also, maybe you are asking, I have a lot of data, right? So I care about vision applications. I do have a lot of data. Why I have to care about regularization and small and noisy data, right? So I think the answer here is that actually, even though we have a lot of data in many cases, right? So this unnatural data set is actually pretty big. There are like 1 million examples. However, still, partly we're in a noisy and small data set regime just because of the imbalance and heteroskedasticity, right? So you may have big data for many of the classes, but still there are some classes with small data, right? So some of the classes only have like 10, 50 examples, even though some of the other classes you do have very big data. So that's why we still have to care about this kind of small and noisy data regime and apply this regularization technique in some clever way, because we have to deal with this small special part of the region where you have only small and noisy data. And we have talked about regularization, and the next question is how much do we regularize, right? So how do we regularize and how much do we regularize? So maybe let me just revisit linear regression just to get some intuition about how do we regularize a model. So this is a very classical linear regression, you just have y is equals to theta star transpose x plus some c, which is the noise. And let's say sigma square is the variance of the noise. And then if you do just the classical ridge regression, you're going to have L2 regularization on the loss function, which is lambda times the L2 norm of theta squared. And the classical learner theory will tell you that the optimal choice of lambda should be on the order of sigma squared over n. So sigma squared is the variance of the noise, and n is the number of examples. The point here is that you want to be regularizing more if you have more noisy labels in your data set, and also you want to regularize less if you have more data points. So the same kind of like a trend or story is a little bit less understood for deep learning. So we don't have an exact derivation of the optimal choice in deep learning. However, the trend of the regularization strength is similar. Noisy and small data set means that you have stronger regularization. So this is the principle. Let me just write it again in this new slide again. Noisy and small data means we should use stronger regularization. However, the story is a little more complicated, as we have talked about, right? So imbalance and heteroskedasticity means that you don't have a uniformly small and noisy data, right? So some part of the data is small, and some part of data is big data, right? And also some part of the data is pretty clean because those examples probably are very easy to label, but some part of the data are very noisy because those are very hard examples. So we have to be a little more clever about how do we use regularization. So here I'm using a toy case to demonstrate why we have to be clever about it. So here I have a imbalanced and heteroskedastic one-dimensional data set. So on the left-hand side, I have big and clean data, right? So you can see that here the blue curve is the ground truth, and the dots are the examples, right? So you can see that on the left-hand side, you have a lot of data points, and also there's almost no noise in the data set. On the right-hand side, we have small and noisy data set because we have a lot of variances there, right? So now suppose you use a regularization technique, and then you get into this dilemma about whether we want to use strong regularization or weak regularization. So let's say suppose you use weak regularization, which is the orange curve, then you can see that you fit the left-hand side pretty well. However, you don't fit the right-hand side. You also fit the right-hand side very well, but you are overfitting to the right-hand side. You don't have any denoising effect on the right-hand side. However, if you use strong regularization, then you are going to underfit the left-hand side, even though you do have a reasonable denoising effect on the right-hand side. So there's a dilemma, right? Strong regularization works pretty well for small and noisy data, and weak regularization works pretty well for the big and clean data. And which one you want to choose? The solution we provide is that we want to use adaptive regularization so that we can regularize different data points differently. So we want to use a different regularization strength lambda I for each example xi. However, here there's a promise. The premise here is that you need a regularization that does depend on example x, right? Suppose your regularizer is just an L2 regularizer, then it doesn't depend on what you put on in front of the regularizer, right? At the end of the day, the only thing you care about is the sum of the regularization strengths, over the entire data set. However, if you have a regularizer that does depend on example x, then the story is different, right? So your regularized loss will be the training loss plus a sum of lambda I times r of theta comma xi. And what are these kind of like adaptive data-dependent regularizers? I'm going to introduce one, which we are going to use in this talk. So in the next slide, I'm going to introduce one choice of this data-dependent regularizer. So now the principle, again, is still noisy and small data points will imply stronger regularization. And actually, we did some theoretical derivation on how strong you want it to be. And this is only done for one-dimensional data. So for one-dimensional data, we derive that the optimal regularization should be lambda I is equals to I sub I to the power of 3/5 over Q sub I to the power of 2/5. So here, I sub I denotes the uncertainty of the label of xi, and Q sub I measures the density of xi. And in parallel, you have to figure out some ways to measure the I sub I and Q sub I. But if you have those, then you can just do this regularized version of the loss, and you optimize the regularized loss. And here, let me just clarify that the exact formula here probably does not matter that much, because we are doing a lot of approximations when we derive this formula. So we have one-dimensional data sets, and we have this non-parametric family of problems to derive to make the math feasible. However, the same formula may not be the best for high-dimensional model, even though still we are following the formula pretty strictly in our experiments. So I can imagine that some other variants of the formula could potentially perform better. And if you use such a regularization for this one-dimensional problem, you're going to see that now, because on the left-hand side you have small and clean data, the lambda I will be smaller. On the right-hand side you have noisy and rare data. The lambda I will be bigger. So you regularize much more on the right, and you get this better curve where you don't underfit on the left, and also you don't overfit on the right. So now let's talk about a little bit more about the algorithmic details. For example, what regularizers we're going to use. So the regularizer we're going to use is a data-dependent regularizer, as we alluded to. So this is a regularizer that depends on both theta and x, and effectively it's just measuring the Lipschitzness of this network, even though inspired by one of the prior work in my group, by my student Colin Wei and myself. So we are using a slightly variant of the Lipschitzness of the model. We are actually measuring the Lipschitzness with respect to all the layers of the hidden variables. So this makes the regularizer even stronger. So, but if effectively it's a Lipschitz regularizer. And also we have to estimate uncertainty and density of each of the examples. And what we do is that we group the examples together so that we can only estimate one uncertainty and density for each group. And the group is just defined by the classes. So basically, for each class, we're going to use one number for uncertainty and one number for density. And so for if xi is in the class J, then the uncertainty will be the average validation error for all examples in J. So there's a precise definition of uncertainty in our paper, which is the feature information of the example. However, here we are doing a lot of approximations to reduce it to the validation error, which is easier quantity for us to estimate. I can imagine that there are other ways to estimate uncertainty in the future. So, and Qi is just the size of the class, the number of examples in the class, because that's the Qi is supposed to measure the frequency of the example. And then after you have these two quantities, you just compute the lambda I. And also another note is that we realized that the precise estimation of these numbers are not necessarily that important, because partly because this is a regularization, this only affects the regularization stress, as you may have seen in the other settings, right? So the precise regularization stress is a hyperparameter which may not be as critical as the weights of the examples, right? So even you have like a misestimate some of the numbers by a factor of 2, it wouldn't be day and night. So this is one of the advantage over reweighting techniques, because here to estimate the estimate of this uncertainty and density are not super sensitive. We have done a lot of experiments to verify the ideas and show that they can be better than many of the strong baselines. So let me just briefly introduce some of the experimental setup. So we have designed this heteroskedastic CFAR, where we try to simulate real-world ambiguity in the labeling process. So what we do is we exchange labels between classes cat and dog, 40% of the labels, and also we exchange 40% of labels between truck and automobile. So this simulates the real-world ambiguity, because cat and dog indeed looks relatively similar if you have only like CFAR's resolution, and also truck and automobile are pretty similar to each other. We also have a heteroskedastic and imbalanced version of the CFAR, where in addition to the heteroskedasticity, we also downsample 5 classes to make the dataset have 5 rare classes. And also we work on one of the natural heteroskedastic dataset called web vision. So this is a natural web-sourced imbalanced and heteroskedastic dataset. And also we have some synthetic NLP datasets and some other vision datasets as well. So some of the baselines, let me introduce them. So we compare with 3 types of algorithms. So the first type is the so-called noise cleaning type of algorithms. What they do is that they train networks to identify clean examples and then focus more on the clean examples. This includes co-teaching and IPCV. And the second type of examples is reweighting, which means that you use a teacher network or meta-learning to determine the weights in front of the losses. And the third type of example is the so-called robust loss type of algorithms, where people design new loss functions that are more robust to label losses, to label noise. And also we have some ablation study comparing to the vanilla empirical risk minimization with the same weights on all examples, and also the uniform regularization where we put the same weight in front of the regularizers. So the first experiment, Heteroskedastic CFAR. So here we compare with a bunch of baselines, and also we compare with the uniform regularization technique where we put the same regularization in front of all examples. And we can see that even just using the regularization, the same regularization in front of all examples can improve upon many of the baselines and be comparable to the previous best method. And if you make the regularization strength more depending on the noise level and the density, then you get this our method called HAR, heteroskedastic adaptive regularization, which improves upon the uniform regularization by another like 5% for the noisy examples and by a few percent for the clean examples. So here I think the main contribution or the main improvement come from improving the noisy classes, because by using this adaptive regularization, we are allowed to put stronger regularization on noisy classes. And also, this is experiment on imbalanced dataset. So here, the baselines are some of the weighting techniques called, and also one of the prior work by my group, also by Heidi, who is the first author. So this LDAM DRW paper is the technique we introduced in the prior work, which also has a similar spirit. So there we try to regularize the rare examples by a larger margin. And we can see that this new heteroskedastic adaptive regularization also improves upon the prior works by a few percent for this imbalanced CFAR data set. And also, we can also combine the heteroskedasticity and imbalance together on CFAR, and you can see that, again, we improve upon the baselines, and also the main improvement comes from that we improve upon the noisy and rare classes. And also, finally, we work on web vision, which is a natural data set without any syntheticness. And what we do is that the first thing we do is that we compare different regularization strengths, uniform regularization strengths with our adaptive regularization. So if you tune the uniform regularization in the best way, then you're going to get something like 60. So I guess you have this kind of trade-off between the accuracy and the validation accuracy, the training accuracy and validation accuracy, right? If you have stronger and stronger regularization, then you're going to get worse and worse training accuracy, but you may get a little bit better and better validation accuracy until it plateaus. So, however, if you use adaptive regularization, we can get better training accuracy and also better validation accuracy, just because we can use stronger regularization for those places where you can use stronger regularization, and also we use weak regularization for those places you may underfit. So, and also we compare with some of the prior work that we can implement and run in sufficient fast time, and we see we can get better results than the prior works. Just to have a summary, so the main idea of this talk is to use adaptive regularization techniques for imbalanced and heteroskedastic datasets. And looking ahead, one of the open questions is that how do we estimate the uncertainty better? So currently, the way we are estimating uncertainty is just using the validation error on a holdout validation dataset. However, there could be better ways to estimate uncertainty. And also, our theory only applies to one-dimensional problem, which is pretty limited, and we need more precise theory for high-dimensional problems. And also another note is that these techniques, these regularization techniques, as many other regularization techniques, are mostly useful when there's overfitting, right? So they are not as useful for larger data sets and moderate size models where there's not a lot of overfitting, right? So suppose your data set is really, really large and you are not using a gigantic model, then maybe this kind of techniques won't be super useful for you. And one of the way to kind of like make it better is that you say, maybe if you have a very large data set, then maybe I should use even larger models. This is actually what people tend to do in the modern deep learning area, right? So you scale your data set and the model together to get the best results. And we do believe that, at least I hypothesize that our techniques will still work there if you have some amount of overfitting. However, this is not always possible, at least not always possible in academia. So maybe we should also think about how do we balance the train and test in the regularization, right? So suppose you already have some underfitting, you already don't have like a perfect training accuracy, you still want to use some regularization in the right way, then how do we balance the training error and test error? I guess these are all I want to say. Thank you very much for watching. I'm looking forward to talking to you in the live session. Thanks.